We will start now with the first presentation of Peter. So I have closed my screen.
Yep. Here we are. So do you see my slides?
Yes.
Yes.
A second. Maybe that's better. Like this? All right. Good. Thanks a lot for the invitation to join you today. I hope that I can inspire or inform you about what I'm doing. My topic is multi-system modeling and digital twins. And the reason why I'm working on that and why I'm here in this panel is we have a number of projects in preparations, but also up and running already, where we have different sectors combined. For instance, the pumping stations in Holland and the electricity sector and the markets for energy. Yeah? So the consume energy and the rain in Germany backfires 24 hours later in the pumping load of the channels, because let's not forget we are below sea level here, so we permanently have to pump, and that's a sector coupling of different systems. Also with the food value chain from the production in the greenhouses over food processing, how they interact and how they can find synergies, find or quantify risks and points for optimization. And that's this multi-system modeling topic. I'll give you an example of the Rotterdam harbor, a very complex example. It's not only the largest harbor in Europe, but also a huge business park with all kinds of factories and buildings and food processing and cooling and petrochemical and pharmaceutical industry. And they are in permanent need of insight, because they have an ambitious goal to be the green harbor of this planet. Yeah? They have to compete with the Shanghais and so forth. And their goal is to compete with sustainability. So everything that happens there, logistics, food, everything needs to be green in a couple of years or decades. And the situation is very complex, and we are helping with modeling. So we model all the electricity networks and heat and gas and steam, transformers, hydrogen, hydrolyzers, and whatever you find there, including all the processes in the buildings and the factories. And with these numerical models, we try to support the decision making. Because with paper and pencil and with a plain eye, you don't see the dependencies anymore and the synergies. It's too complex. Yeah? And we use an armada of software there and sophisticated modeling languages. And with that, you can optimize in the planning. Yeah? So what you will do in the future, but also in the controls on the fly in real time if your models are quick enough. But what we see there is it's quite complex, not only because the data is sometimes private and different stakeholders, and that's very tedious, but also the models we need are very, very peculiar and often fundamentally incompatible. The four examples that I give you here are the classical ones, but there are more. Most of the physics we can describe with differential equations. Yeah? So you take a textbook and you know how it works, and you have the parameters, and then you can describe them, and then you can let a computer execute the model for you. That's a continuous physics. Everything with computers, IoT, sensors, digital controllers is discrete. So they make decisions, they switch, and that's typically done with discrete models, state machines, queuing theory, also communication networks. Everything that is a role, a player, yeah, is a behavioral model. Now, there are also specific description methods for that. And sometimes you do it with game theory, if it's just a few players. If there are more, you might use a multi-agent system. Again, this is a different world. And you can also have stochastic and statistical phenomena. You know, the weather is just the most simple example, but there are even more. And they all come with their own mathematics, with their own people, with their own university degree. And it's important to bring that together. Yeah. And the way how we do that is on one side a lame workaround, because there is no universal language that can do it all. On the other side, it has a number of fantastic advantages. So what we do is we decompose the system. Here I give an example of car charging, because everybody knows what that is, into its elements. And we get an expert for all these elements: battery expert, the car driving expert, the car charging expert, the grid expert. And they come with their own models, in their own language, in their own modeling philosophy, with their own data, and with their own software. The only thing we have to do is to hook them up, yeah? Connect these things so that they dynamically influence each other. Yeah? Because it's not a one-way flow of causality, it's a mutual dependency. And that needs to be solved numerically. I will not go into the details there, oops, because that's quite complex. More important is how to interface. So there are a couple of standard or not standard interfaces. We are still in the development phase of this discipline, but manufacturers of software already jump on it. So this FMI is one of these things that you could remember. It's the functional mock-up. It comes from automotive and avionics industry. They have developed it, and we are now using it also for other domains. So this allows us to couple software, yeah, for a grid system and for batteries and markets and so forth. So you can couple these things. Even with different computers, they can be distributed as well. And the nice thing, and now come the advantages, you have lots of details because you have a multi-focus. Yeah, you don't have to compromise on accuracy anymore. Normally, if you are a scientist in a certain domain, for instance, you're in water management or in electricity, you have your own tools. And if you say, oh, my system is interacting with other systems and I have to use them and I have to cover their dynamics as well, because I'm not alone, you normally simplify it. You squeeze the other properties and dynamics into your modeling philosophy, and then you make mistakes. It's lossy and it's wrong in the end. You cannot validate it. It's a nightmare. Here, not the case. You take the models as they are maintained by experts since decades, and everybody's happy with that, and they are validated, and industry relies on it, and so forth. You don't have to reinvent the wheel. You're reusing things. And by that, you don't lose the accuracy. So if I'm optimizing a market, yeah, if I'm a market guy that tries to make a fair and performant and quick converging market, I don't do this on top of the battery. So if the charging is very, very harmful to the battery, I wouldn't see this in my market simulation, but the battery simulator would tell me. So all these little details that could kill the system in real life, you also see it there, because there is no loss of accuracy. Oops. Another thing that we saw is a dynamic step size control, because our problems in systems of systems, some phenomena are very fast, seconds, or even faster. Others are minutes, hours, days, decades for investment planning and economic effects and so forth, and weather. And there is no one model fits all, but with that setup, we can come close, yeah, because we have dynamic step size control. If things are happening fast, it steps down very fine. And if things are more relaxed, it goes into larger steps. So that is a very nice feature. And we have all the cyber physical elements as well, yeah? Because the digital transformation, let's remember, digital transformation is the reason why everything is connected nowadays. Yeah? That's why we can have water and food and electricity and markets and so on seamlessly interacting, yeah? Because we have the data, we have the connections, and on top of that, we can make all these applications. But if there is something going wrong in the ICT, yeah? Packets get lost, cyber attacks and so forth, we would like to know how big is the risk. Yeah? Is it collapsing, or is it fine, or is it just getting a bit degraded? And with these models, we see it. Yeah? We can really try it out. We do these experiments with humans in the loop. So we have hackers in one room and the defenders in another room, and you see how your system reacts to it and how you can improve it and so forth in the end. So that multi-system modeling brings people together and shows you, hopefully, what is happening out there. Because in reality, the models are also connected and dynamically interacting. We just have to imitate this in our setups. So that's the next thing. Full-fledged setup of all the physics, of all the ICD and all the humans in the loop in control rooms and in users and so forth. And that's typically called a range. It's like a golf driving range where you practice your golfing. This is a cyber range is called when you practice operations in the digital world. And if we include all the physical things, logistics and so forth, then we have this cyber physical range. That's what we're currently setting up. Very much focused on electricity, of course, because we're the power system department here. But as we work on integrated energy systems, we are making interfaces to the other systems that we are interfacing with, the water system in Holland or markets and so forth, and inviting colleagues to attach themselves and to join this effort. That was multi-system modeling. Now, digital twin, you might have heard about it because unfortunately it's a buzzword this year. It was easier before, it will hopefully be easier next year. But 2020 is a digital twin buzzword year. Everybody is crazy about it and thinks he has to do it. Basically, it's a numerical model, as I've described it before, but you have a lot of helper programs around that get data in and out. And often this data is real time. So there's a stream of data from reality, from your system, feeding your replica, and you can see what's happening. You can compare it, discover anomalies. You can maybe fast forward and look into the future, what would happen. You can go into scenarios and sweep over parameters and assess the risk and come up with robust decisions. That's the promise of these digital twins. And we are working on that as well. And I believe they will be ubiquitous someday. So it's not only in the cloud, big data center twins, but maybe even in the devices, in the substations, in the controllers that they use this principle. The most prominent example of this program here is that we want to replicate the entire Dutch electricity system in a supercomputer. It costs many, many million euros. I'm currently collecting the money. So if you have something to spare, call me. We heavily invest into this computing hardware and also in the models and doing that with students and with projects. And by that, we want to have a playground for everybody who's interested in what can we do in the future to decarbonize our society. Is it safe to connect this and that? Because there are heavy investments into offshore wind and photovoltaics and connections and new markets with blockchain and so forth. And nobody can tell you if this really works, if this converges, if it's safe and so forth. It's such a twin we can just try out and explore all the risks and let it do the number crunching for us. It will be connected with our control room of the future, where we do these attack games between the blue team and the red team. And we try to connect with other institutions in this respect. So we want to do it open source. And if you're interested, then please contact me in that as well. So bottom line of multi-system modeling and digital twins, as I said, it's a methodology. It's a workaround because we cannot model it analytically anymore. There is no swing equation for a cyber physical discrete system, doesn't exist. And so we go for a numerical way where we connect dynamic simulations. And this usually serves as a platform, as a shared space for a multidisciplinary team. Policymakers, consultants, scientists, users, all the stakeholders can come together and express their constraints and needs. And then you can try it out. You can let the machine search for an optima, and then you can discuss it because it gives you hard facts. And that helps a lot because often these multi-system situations are very complex and everybody's emotional about it. And if you don't have hard facts, it's hard to discuss. And that's the contribution of these models. Of course, they are not easy. I told you only the good things now. There are a lot of difficult accuracy, performance, error propagation. It's really not that easy. But we are working on it, not alone. It's an international community that does that. And I'm very convinced that it's a very useful tool for system analysis. In the end, what we see now in the last years, a lot of AI comes in, how to generate the models, how to interpret the data, how to explain them. So lots of machine learning that helps a lot. In the past, it was all manual, self-done. That doesn't scale well. So in the future, we hope to automate a lot in the workflow of getting such a multi-system model and a digital twin. Thanks a lot. I hope that was in time, and I hope that it means something to you, and maybe you can use it in the future. Thank you. So how do I stop this now?
Okay, thank you very much. And